Are you ready to go? Okay. So we are happy to have Yilin Wang for her final lecture on last deviations of SLE and Weil-Petersson Teichmuller space.
Okay, thank you very much. So today this is the last talk, and my goal of today is to tell you how some results from SLE will give you some results about Weil-Petersson Teichmuller space. So this is, I just recall that on the left column that you see those are subjects, a probabilistic field, a field of probabilistic objects using like Schramm-Loewner evolutions, they are random curves. But on the right-hand side, those are deterministic objects like containing Weil-Petersson Teichmuller space, Weil-Petersson quasi-circles, the Kähler geometry I tried to explain last time. And for today, what all we would need to know from SLE and this relationship to Weil-Petersson Teichmuller space, let me just recall you that how the story was that. So all you probably need to remember is that this Loewner energy tells you about the large deviation rate function of the SLE when kappa goes to 0. Right? This is measuring how rare an SLE with small parameter staying close to another curve, how that probability decay when kappa goes to 0. And this Loewner energy is the exponential decay rate of that quantity. And in the last lecture, we generalized the Loewner energy to Jordan curves, and then the loop energy is a number that is measuring how round the curve is. So this energy is 0 if and only if the curve is a circle, and it's a Möbius invariant quantity. It generalizes the Kodo energy. And the most important result from the Tuesday's lecture is saying that this loop energy, which first was determined using driving functions by taking limits when shrinking by passing from the chord to the loop case, can actually be written just in the form of very simple 4 terms where there's the L2 norm of the pre-Schwarzian, etc. I will recall that number later on. And we also showed you that the Loewner energy is finite if and only if gamma is a Weil-Petersson quasi-circle. And there's also another 25 equivalent definitions of this class of Weil-Petersson quasi-circle. So today, the topic is more coming back to the probabilistic side, as this is the field that I'm more familiar with. So the first, I will tell you what is going on when I'm taking the kappa parameter goes to infinity. This is called SLE infinity large deviation, but we will use a version called the radial SLE version. And then we'll study some relation to Weil-Petersson quasi-circle. All right. Just the motivation that we have seen that when kappa is small, that there's when kappa is less than 4, we have the curve, the Kodo SLE is a simple curve almost surely. When kappa is between 4 and 8, it's a curve which is can touching itself. So, but when kappa is greater than 8, it becomes a space-filling random curve. There is a remarkable feature about SLE in the SLE story is that so-called SLE duality. If you take a kappa greater than 8 in this picture, that the duality actually works for any kappa greater than 4. But here, let's just take the case when kappa greater than 8 is a space-filling curve. And if I stop at a certain time and look at the boundary of this cluster, so you can imagine the larger kappa is, the more this the tip of the driving function, the curve will wind quickly on this real line, and the curve is oscillating faster. And then it will make the boundary actually straighter. So in fact, the boundary of this SLE kappa cluster, if you zoom into it, it locally looks like SLE 16 over kappa curve. So to make the statement precise, I won't make this statement precise, but this is just the idea. But that would suggest that if we know some asymptotic behavior of SLE 0 plus, which will give rise to this Loewner energy, and SLE 0 plus will be dual to SLE kappa when kappa goes to infinity. And that led us to study the large deviation of SLE infinity, and that will give rise to another energy, another rate function we call the Loewner-Kufarev energy, some large deviation result. And because this duality between SLE, it suggests that Loewner-Kufarev energy should be dual to Loewner energy in a certain way. So today, this lecture would be one example of how results from the random conformal geometry-like studies of SLEs can give you some information about the space of Weil-Petersson quasi-circles. This is one example of that. Well, let's just start slowly. Just in this picture of the Kodo SLE, what happened when we let kappa go to infinity? And let me just recall you how was the Kodo SLE was defined. So the SLE kappa is the Loewner chain driven by square root kappa times Brownian motion. And what it does is that this is the driving function WT, and WT is moving on the real line. And this is a vector field which has a singularity at the point where the driving function is. So this vector field is like 2 over z minus this driving function point. So here it's pushing down very quickly, if you just right above this driving function here. And for the other points, it's pushing away from the singularity. And in order to find out what the SLE kappa is, you solve for each of the point in the upper half plane this differential equation with initial condition C. And there is a maximal solution time. It could be infinity if it's never swallowed by this growing house of KT. But here, actually, if in the case when kappa is greater than 8, this tau will be always almost finite. So this is a maximum solution time that of this differential equation, and HT is all the point in the upper half plane such that tau z is strictly larger than t. Right, so this is the set of points where GT is well defined. If the solution exists up to time t, then this GT is well defined. It's actually exactly the domain of definition of the conformal map GT. And this is, if you look at the complement of HT in the upper half plane, this part is the SLE up to time t. Right, so let me just draw a picture. So here you will have, just to remind you, so this yellow, the orange part, this part is gamma from 0 to t, and GT is the map which will send the complement back to the upper half plane. And now what do we do when we let kappa go to infinity? So when kappa goes to infinity, this driving function will move quickly away from any point C. Right? And this vector field is going to converge to 0. So over a fixed time interval from time 0 to t, you can see that GT of z for fixed t and fixed z, but letting kappa go to infinity will converge just to z. And that is saying that this mapping out function GT, it converges to the identity map. So in the limits, when kappa goes to infinity, GT is going just to be the identity map, which is not going to mapping out any compact set. So the limit of already taking the kappa goes to infinity is not so interesting in this Kodo case. Right, so it's not very interesting. So the issue is actually because if you look at this differential equation, it's actually giving you this family of conformal map GT, which is normalized at infinity. So GT's expansion at infinity will be like identity. And also where the points, the driving function is moving, it can get arbitrarily close to this normalization point. That's actually what's happening, it's actually why this limit is the trivial limit. So it's not so interesting by letting kappa goes to infinity in the Kodo setup. That's why we switched to a radial setting of the Loewner chain. It's actually the radial Loewner chain that has been introduced by Loewner, this original version of Loewner. But I will just introduce you this more general version of a Loewner-Kufarev equation that will be a Loewner chain normalized at 0 inside a unit disk, but driven by family of measures. The setup is the following. You look at this family of measures, so they're always indexed by positive time. Each of the rho t is a probability measure on the circle, and its dependence on t is measurable. Or if you want, you can view rho as a measure on the cylinder where of the S1 times the positive real line. And this rho t is the disintegration of that. We can just use this one. The Loewner-Kufarev equation is the following. Right? So instead of, I will first describe this family of the Loewner PDE. So this is a family of conformal maps which will send in the unit disk to some subset of the unit disk, which contains 0. Right, so the Loewner-Kufarev equation is as follows. So if we take any point in the unit disk, looking at this differential equation with starting point z equal to z, f not z equal to z. Wait, how to understand this differential equation? So here, rho t is a probability measure on the circle, and this is a complex, this is a holomorphic function depending on z. Right, this is a holomorphic function that is from d to the point of z where real part of z is greater than 0. Right, this is sending the unit disk to some set of positive real part, so the right half plane. And now, if I multiply by minus z, multiply by also by f prime of z, it is giving you a vector field which is going towards inside of the domain. So if you just ignore this term here first, this is a function with positive real part, you multiply by minus z, so it is taking value towards inside. So if this point is z, all right, you turn by z and multiply by z and then take minus. All right, and now if you multiply by f prime of z, this would be a point. This is vector field will be pushing towards the inside. So now, if you start from ft of z is here, so the vector field is pointing towards inside of the domain. So you can see this is a differential equation which was going to tell you its time evolution is given by a vector field which pushes towards inside of the domain. All right, so this is the differential equation that is for each of z, this solution exists for all time. And what you obtain is that ft will be a map from the unit disk to a certain domain, simply connected domain dt, with ft 0 equal to 0, and its derivative at 0 is exponential minus t. What it says is that this is one illustration of dt. This has conformal radius exponential minus t. So the way to think about this is that I'm giving a family of probability measure. This will be equivalent to as if giving you a family of conformal maps to a shrinking family of domains in bigger domain dt. So these are, if you know what is this evolution family dt, you can also write down what is ft by Riemann mapping theorem, and you can also obtain this rho t. So given this, one of these three data, they're the equivalent. And here, this is the, so one way to like visualize what is this evolution here more explicitly is that if your measure itself, this rho t has a density with respect to Lebesgue measure, then the normal velocity of this boundary of dt is normal to how much it moves from towards inside. That is exactly given by 2 pi this density when, and then you scale by ft prime. So if the rho t is just a property measure, it doesn't need to be strictly positive everywhere. So if rho t is 0 on certain part of the boundary, so that will tell you that, say, if this part of boundary corresponds to this part of boundary, if rho t is 0 on this part, then it means that dt is going to get to inside, but its boundary will stay put here. It won't be moving inside from there. So in the end, what we obtain is this evolution family dt. They're monotone, but might not be strictly monotone. The one for larger t, you're contained inside the smaller t dt, but the boundary might coincide. And to relate to a little bit the caudal setup is that if I look at the inverse of ft, this will be also a conformal map from dt back to the unit disk. It will satisfy this differential equation. Now it's an ordinary differential equation, and it's in this form. So this is, if you want, you can also just start with rho t and you can write down this family of solution of this differential equation. But now for each z, there is a certain maximal time for the solution that exists. And so dt would be the collection of set of points where the solution still exists after time t. So these two ways are equivalent to view this. All right, so if you don't remember about how this differential equation is looked like, why the map ft is 1-to-1. All right, so the reason that it is 1-to-1 is also that you can look at the backwards time evolution. Right, okay, so you can also write down its backwards time evolution. And yeah, I think if there's a backward time evolution, then it's 1-to-1. Okay. Yes. So just an example, let's probably show you why this. So in the case, the trivial example is that when the measure itself is a uniform measure, Lebesgue measure on the circle for any time, then dt will be just a shrinking disk. And now if I take this measure to be a moving Dirac measure, then so now the measure itself is Dirac, is moving on this boundary. And what you obtain is the radial SLE kappa. Right, this is the definition of radial SLE kappa. So in the case you have the same phase transition when kappa is less than 4, you have almost surely this curve is a random simple curve from the starting point. It starts from 1, heading towards 0. And when kappa is between 4 and 8, it's touching itself. It can come around here as well, go around. And dt is the complement. So dt is the part that's in yellow here. And when kappa is greater than 8, it's almost surely space valid. All right, these are two examples. And you can see this example, they are quite different. So this one, the measure itself is a continuous. It's a Lebesgue measure itself, so it's continuous. So it's growing from everywhere from the boundary. But for SLE, so when here is you have a Dirac measure, and then it's growing only from one place, right? And all the other, say in this picture, all the points from on the boundary here, they might be moving along this. Moving along the boundary on the circle, but they are not going to move inside. So now if we let kappa goes to infinity, what would happen? Right, let's do this computation. Like we call this rho t is this Dirac mass with variance, Brownian motion has variance kappa. From time t to t plus delta t, if I look at this GT satisfied this ODE, so it's a little bit simpler. I will just do this. How much it moves is integral from t to t plus delta t of gs of z. This is just putting the vector field multiplied by the Brownian motion b kappa t. Right here, this should be kappa s. ds. And now if I just do this approximation, if delta t is really small, and for a point z that is, I pick inside the disk, so this is of a certain distance away from the boundary, you can imagine that this gs is very well approximated by just gt. Right now, these are functions that doesn't depend on s, and using Fubini, I can exchange this integral from here to here. And what you obtain is this approximated by gt of z multiplied by the same vector field, but now you first integrate this Dirac mass over time, a small time, from t to t plus delta t. So what you obtain is just the increment of the occupation measure of the Brownian motion. And as kappa goes to infinity, this occupation measure by Ergodic theorem is going to converge to the Lebesgue measure. So what you obtain is finally just the Lebesgue measure. And after integrating this part here, you will have dt, just dt of gt of z. And what all that shows is that this heuristic argument is telling you that this time derivative of gt is gt itself. So we obtain from the original initial condition, gt of z is exactly exponential t times z. This is the map, which is only defined on this dt, that's a smaller disk, back onto the disk. So in the end, what we show is that this second example, when I let kappa go to infinity, the Loewner chain that is generated converted to the Loewner chain generated by this example. And actually what we have used is simply this measure. Now this measure is viewed as a measure on the cylinder. Is a moving Dirac mass integrated over time, converges weakly to the Lebesgue measure. And this is all we have used. And you can also see that because this is the function that you integrate against is a function that is, you have a nice control over what this function is. So it's exactly from the weak convergence of the measure here, you get the weak convergence, you get the convergence of the Loewner chain, the family of conformal maps. All right, so here are another maybe visual to visualize it. Here I just draw the picture of occupation measure. You can see the time is here, circle you have the Dirac mass that is moving on this, moving up in like a Brownian motion. And when kappa goes to infinity, it converges weakly to the Lebesgue measure. And also the result about SLE large deviation principle is actually in the end boils down to large deviation of this occupation measure. So for that, we will use a result by Donsker-Varadon, and I will just state it directly in the language of radio SLE. This is a joint work by with Maurice An and Jay Park. They were from last year, and they're graduate students at MIT. And what we showed is that the radial SLE kappa process satisfies the large deviation principle as kappa goes to infinity with rate function with S plus, as we call the Loewner-Kovarev energy. And this definition is here. But here, this result, heuristically, it means that if I'm giving a family of rho, this measure is a certain measure. We call that for rho t, each disintegration for each fixed time t is a property measure. The SLE staying close to this Loewner chain driven by rho, this probability decays very quickly when kappa goes to infinity, but the decay rate is this number S plus, the Loewner-Kovarev energy of rho. And so this is the heuristic, but you can also like write down it's using the usual large deviation principle, which will say for any open set, any closed set, you will have the probability, log of probability time divided by kappa, limbs in, limbs up, going to. So this is the standard, there's a standard large deviation principle, but I will just state this version here. All right, how this Loewner-Kovarev energy is, it is written as some integral of L of rho t. And well, L of rho t is defined as follows. If rho is absolutely continuous with respect to Lebesgue measure, then I write this density as nu t squared. L of rho t is the Dirichlet energy of nu t. In other words, it's Dirichlet energy of the square root of the density of rho t. And we set this energy to be infinity if a rho is not absolutely continuous with respect to the Lebesgue measure. All right, so here this energy is finite for very regular measures. It first has to have a certain density with respect to Lebesgue measure. And for instance, if you have a Dirac mass, then it's automatically infinite. And this result actually follows from Donsker-Varadon theorem, which is a result about the occupation measures. And so their result is for occupation measure for a fixed time. All we had to do is to prove the one for the integrate as a process of occupation measure in T, and we just obtain this result. All right, so in my first lecture, I also already told you that the large deviation when kappa goes to 0 case, it led to a family of curves with finite Loewner energy. And those curves, they're much more regular than SLEs. And here we also see an example of when we look at the large deviation rate function, the objects we look at, they're more regular than the measure that you start with. We started with the Dirac mass moving along time, but in the limit already we see the measure becomes Lebesgue measure, and even for the large deviation principle, the measures with finite rate, they're absolutely continuous. You see another regularizing phenomenon happens here. So now the question, now we see what is a large deviation, SLE infinity large deviation, and we ask about what are the family of DT generated by finite energy measure? And this is the second part of my talk. And that was giving you some duality between Loewner-Kovarev energy and Loewner energy. And just in order to provide a bit more of symmetry, I will upgrade this Loewner-Kovarev equation to a whole plane version. So it will be defined for a family of measure where time is parameterized by all real numbers, not only positive ones, but also negative ones. And what you obtain is a family of shrinking simply connected domain containing 0 with conformal radius exponential minus t. So you might not see the unit circle anymore. So this is just a shrinking family of simply connected domain. But it can be also related to Loewner chain in the unit disk. So this will be defined such that if I fix S and I map inside of ds to the unit disk, then this foliation that you get here, this boundaries that you get here, or the shrinking family of domains you get, will be exactly the Loewner chain generated by rho t plus s. So the family starting from time s. And we also define the Loewner-Kovarev energy for such a family of rho by like integrating from minus infinity to plus infinity of L of rho t. Okay, if you're not happy with this, you can also think this, think just in terms of the Loewner chain in the unit disk. It's actually a special case of this whole plane Loewner-Kovarev chain. So if you have just given some positive time probability measures, and we can set this measure to be a uniform Lebesgue measure like for negative t. Then what you obtain in this whole plane setup is that, so for any negative time, you will just get concentric disk with the correct conformal radius. But for positive t, you'll get the original family generated by rho t, with positive t. And the reason of using this whole plane version is that we don't want to emphasize the special role of the circle. And also you will see there are more symmetries, inside and outside symmetries. So our first result is that if the Loewner-Kovarev energy is finite, then each of the boundary of this dt is a Weil-Petersson quasi-circle with no exception for all t. Right, the second thing is that the union of this boundary covers the whole plane. You cannot sweeping out the whole plane without leaving any bubbles unvisited. So it's really moving continuously in some supernorm for some type of some parameterization by component. But this is the most important part. So this is what we call a foliation by Weil-Petersson quasi-circle. You have a whole plane that is covered by those Weil-Petersson quasi-circle. But here I put the quote mark for foliation. It's actually a different foliation than geometry will talk about. So first of all, our leaves, so each of this boundary dt is called a leaf. Those leaves are non-smooth, so they're Weil-Petersson quasi-circle. And we call that they even don't need to be C1. All right, and also you have this family, they are monotone, so one is containing the other, but they're not strictly monotone. They can have parts of it overlapping. So it's not the foliation in the classical sense, but we still call it foliation by Weil-Petersson quasi-circle. And this is really what the analogous result by SLE duality, like we call that. This Loewner-Kovarev energy is describing some large kappa behavior of SLE. And here it says that its boundary at the fixed time is a Weil-Petersson quasi-circle, which means that has finite Loewner energy, so which is describing SLE 0 behavior. It's not surprising if you know about SLEs, and this is the kind of thing that you would expect. But however, this is purely a result about there's a certain deterministic measure and it's a deterministic Loewner chain and some behavior about Weil-Petersson quality circles, boundary Weil-Petersson quality circles. There's actually a lot of research on this Loewner chains. Like you can ask about what condition that you can put on the measure and what consequence you can get for this boundary of dt. And this is the only explicit result in the case of non-smooth boundary. I think that is known. Like it's even still an open. It's an open question about what is if there's if and only if condition on the measure which generates quasi-circles. But now we have one for Weil-Petersson quasi-circle. That is really neat. And actually, we can make it even more quantitative. Now, here we have an energy that is Loewner-Kofarev energy. And for Weil-Petersson quasi-circle, there is a Loewner energy associated to it. And we can actually relate these two more quantitatively. So for that, we need to introduce a notion called winding function. So if we start with a foliation of Weil-Petersson quasi-circle, we call that Weil-Petersson quasi-circle, they're rectifiable. So there is almost everywhere a tangent. So here, this is illustration. This winding function, it can be defined using this control method GT, but geometrically, it is measuring a certain angle. So let's say for this point Z, it belongs to a certain leaf because the leaf covers the whole plane. Right? There's always at least one leaf passing through this point Z. And so for most of the point here, there is a tangent. And you can also look at this purple circle, which is center 0, passing through Z. This circle here, and phi is measuring the angle between this green tangent with this circle. This is what we call a winding function. Right, this function is a function defined almost everywhere on the leaf, and our result. This is the main result. All the other results will be a consequence of this one, is that the 16 times the Loewner-Kofarev energy about this family of measure generating this Loewner chain is equal to the Dirichlet energy of this winding function. All right, this is a result saying that, also says that they're finite if this one is finite, if the other is finite. We show not only that one left-hand side is finite and they're equal, but also if the left-hand side is infinite, then on the right-hand side is infinite, vice versa. So this is really the optimal result that we could obtain that could encompass all the cases. And this 16 is also consistent with the SLE duality. Remember this SLE duality was relating kappa to 16 over kappa, and this is the same 16 here. And it will become a bit clearer when we see one of the corollary of why I say this. All right. Are there questions? There are a lot of definition already.
So if the same point passes through more than one quasi-circle, is this winding number well defined?
When the phi is well defined?
Because in the definition of the winding function, we choose a t for which the point passes through the boundary of the quasi-circle at time t.
Yeah.
But you also mentioned that presumably there are more than one t's for which this can be.
Yes. Thank you for a good question. This is a good question. Yes. So if there are several points, because of the monotonicity of domains, if there are several leaves that's passing through this point, the red curve has to be contained inside. So if there is a tangent, their tangent will be the same.
Sorry, what is S overall?
S of rho is here is defined, is the Loewner-Kofarev energy of integral of L rho t, and L rho t, that is this one.
Thank you.
Yeah. Yeah, this is the monotonicity actually, and this geometric interpretation actually will tell you that if there are several leaves passing through this point, they define the same winding function at this point.
But it was ST overall was defined, ST, and now there is S without T?
No, S plus. Here is, sorry, this is S plus of, this is for positive time.
Okay, thank you.
Yeah, sorry, this is, yes, T looks like plus.
Thank you.
Yeah, and S of rho, that is just to distinguish, this is integrating from minus infinity to plus infinity.
Thank you, thank you.
I show you another example than this trivial one. If my rho t is 1 over pi sine square of theta over 2 d theta, so this is a measure which will vanish at 0 and positive everywhere else. And this is actually the minimal energy measure, minimal energy which minimizes the AL function, but which vanishes at 0. So if you look at this measure, and I ask it t to be, for t from 0 to 1 and being Lebesgue measure for other time, then the foliation that you get is this, those are all circles. They're all touching from time 0 to 1, or they're all touching this point. And after time 1, so they're growing by this equipotentials. These are, so the curves that is inside here, these are just imaged by the concentric disk, concentric circle under the conformal map fixing 0. All right. And on the right-hand side, this is the density plot of the winding function. And I think this larger if it's darker and smaller when it's lighter. Already, we can compute what is the Loeffler-Kofarov energy for this measure, and we can also check they're really equal to the Dirichlet energy for phi. But actually, you can try to check that, but even this computation for this very simple example is not totally trivial. But that is just doable. Okay. So now let me just relate more quantitatively the S energy, how that related to the Loeffler energy of a curve. Right, now I'm giving you a Jordan curve surrounding 0, this curve gamma. And I look at the conformal maps from inside this to inside of the curve, fixing 0. And the conformal map from outside this to outside of the curve. Now I'm changing the notation inside called F, outside called F star. And I send these concentric circles also to some analytic curve inside gamma, and concentric circle outside to some analytic curve outside of gamma. And this gives you some particular choice of foliation. So there's only one curve gamma that is just arbitrary Weil-Petersson circle, but all the inside are analytic curves. And this is a foliation, so you can write down it's Loeffler driving function, Loeffler driving measure. And I just call this measure rho of gamma. It's a very special measure which generates the foliation drawn on the right-hand side. The result is 16 times of the Loeffler-Kofarov energy of this measure equals exactly to the Loeffler energy of gamma, but plus 2 times of log of f prime at infinity f prime at 0. This is an identity. And the proof of this result is using the mean result about this relation to the winding function. So the most important observation is that the choice of equipotential will make the winding function harmonic inside and outside of curve gamma. And also recall that the Loewner energy of gamma, it has the form of some Dirichlet energy of argument of f prime. So in last lecture, I say this is the f double prime over f prime. This is the same thing as the gradient of argument of f prime. So this is a function that is also harmonic outside of gamma. It's not exactly the winding function, but we can do some operation to really just using this expression to show that this left-hand side equals the right-hand side. In the end, what you check is that here you have some Dirichlet energy of harmonic functions, and here is also some Dirichlet energy of a harmonic function given by the winding function. Right, this result is relating the Loewner energy of gamma to a certain Loewner-Kufarev energy of a particular foliation. Maybe we can make a more, probably another corollary is saying that it's actually just translating this result. That we have seen 26 definition, equivalent definition of a Peterson quasi-circle, now it's come to definition 27. That the Jordan curve gamma separating zero from infinity is Weil-Petersson if and only if gamma can be realized as a leaf in a foliation generated by a measure with finite Loewner-Kufarev energy. In this direction, say if a Jordan curve separating zero and infinity, we can construct a foliation by this corollary here. So this is just follow from the previous corollary. But in the other direction, if gamma is a leaf of the foliation generated by a certain measure with finite energy, we have this inequalities. So here, this rho gamma, this Loewner-Kufarev energy of this particular foliation or particular driving measure is less than 16 times of the S of rho. The reason is that if you look at their winding function, we call this winding function for this foliation phi and this phi gamma for this foliation, what you know is that they coincide on gamma. Because gamma is a leaf of this foliation here, but also a leaf of this foliation. And this winding function is defined really locally at each point, right? So these two winding functions, they're the same on gamma, but for this one, it's harmonic. And therefore, this harmonic function, they minimize the Dirichlet energy, so you have this inequality here. And for this inequality, actually, we just come back to this identity here. Actually, this quantity log of f prime infinity and over f prime 0 is always positive, always non-negative. This is actually true for any Jordan curve separating 0 and infinity. So as a consequence, we also know that all the leaves have Loewner energy less or equal to 16 times the Loewner-Kufarev energy. That if I want to generate some leaf with Loewner energy less than 16, I just look at a certain measure, any measure with S of rho less than 1, and then generate the foliation, and all the leaves in that will have Loewner energy below this number here, all of them. All right, so here, maybe here you would see more of this connection to SLE duality, right? Because on the left-hand side, this is a large deviation rate function of SLE infinity. This is the large deviation for SLE 0, and there's this related by 16. And another comment is that we somehow need to normalize the conformal map from inside to 0 here inside. And you also have some additional derivative term here. The reason is because that although the Loewner energy itself is Möbius invariant, but the Loewner-Kufarev energy on the left-hand side is always involves both point 0 and infinity. And thinking of you generate the foliation using this Loewner chain, it starts from infinity, it shrinks towards 0. So these are two special points. This is a minor remark. All right, so this is the first consequence. The second consequence about the star theorem is the reversibility of Loewner energy. The statement is one line and the proof is one line. There's some technicality, but I'm hiding that under the carpet. But so the statement is following. I have a measure rho, which with finite Loewner energy. It generates a foliation by Weil-Petersson quasi-circle. And it has a winding function phi. And now I apply 1 over z. I will switch 0 with infinity. Now the orange curves are outside, blue curves are inside. You get another foliation. It has another driving measure, rho tilde. It has another winding function phi tilde. The theorem is saying that these rho, they're very different, but they have the same Loewner energy. The proof is that, all right, let's look at this winding function. We just need to show the Dirichlet energy of the winding function are the same. And using the star, the star, it would imply the final result. But why the Dirichlet energy of the winding function are the same? All right, so phi of 1 over z, phi tilde of 1 over z is measuring the angle. Now this is z 1 over z. We're measuring the angle between the tangent of this point of the green curve with the circle centered at 0. And because 1 over z, they preserve the circles. Right, circle, concentric circles centered at 0 is still concentric circle centered at 0, and also preserves angles. It's 1 over z is a conformal map. So what you have is phi tilde of z equal to phi over 1 over z. And Dirichlet energy is invariant under precomposing by a conformal map. So we have Dirichlet energy of the winding function are the same. That implies the Loewner energy of rho and rho tilde are the same. Well, somehow this is a quite unexpected result, even in view of SLE, because the reversibility of radial SLE for kappa larger than 8 is not known. So we cannot just use the reversibility of SLE large kappa and to deduce this rate function to be the same. Right? In my first lecture, I introduced this reversibility, the proof of reversibility of the Loewner energy in terms of the SLE reversibility. Right? We know about the reversibility of SLE for small kappa, then you deduce the Loewner energy is reversible. But here is a direct proof of reversibility of the Loewner energy. And it also would suggest that the reversibility of SLE, radial SLE for large kappa could be true. And it's not known. All right, so the last 5 minutes, I will just show you, so you can see all the results there following this star theorem, saying that 16 times the Loewner energy equal to Dirichlet energy of the winding function. So in the proof, there are two ingredients. So the guiding philosophy is that Dirichlet energy is a conformally invariant quantity. And the second thing is that the Loewner chain will allow you to explore any conformally invariant object layer by layer. Okay, that's why, like, when people try to study SLEs, they say why Loewner chain is a good tool to study SLEs, because SLE has the conformally invariant property. SE should have SLE, a conformally invariant property. Then Loewner chain will allow you to open up the slit little by little to encode that into a dynamic process. And here we're using the same idea that Dirichlet energy is conformally invariant. Let's use Loewner chain to peel it into layers. More precisely, if you start, so let me just explain the setup in the disk. You have a positive time parameterized family of measure, which generates a foliation of the unit disk. So start with the circle and shrinks towards inside. If you get arbitrary function with finite Dirichlet energy and zero boundary value, in other words, phi is in W1 to naught of the unit disk. And for each of the time t, I can split phi into its harmonic part. This is a function that is harmonic inside dt, and this zero trace part. The zero trace part is a function that is zero outside of dt. This is harmonic inside dt, and this is zero outside dt. And these two are orthogonal for the Dirichlet inner product. And the idea is that we are going to peel phi by splitting them into two parts for each of the time t. So you can then imagine that how you reconstruct phi will be stacking on each of dt a certain harmonic function to get back to the original phi. So to make it precise, that we have the following disintegration isometry. So this is a map from the space of W1 to naught with the norm given by Dirichlet energy. And on the right-hand side is L2 function on the cylinder is 1 times R plus with respect to a measure rho. Rho is the driving measure rho. And this is a map which, okay, you start with a phi with finite Dirichlet energy. You get a function of t and theta. So it depends on t here, dependence on theta is here. And it's not so important how this is defined, but essentially that is what it does is take the normal derivative of this zero trace part. So the zero trace part, by pushing it toward using ft to the unit disk. Now this is a function defined on the unit disk with zero boundary condition, and take normal derivative of this function. So for each t, it will be a function of t and theta. Important thing is that this is an isometry, bijective isometry on this space of Dirichlet, finite Dirichlet energy function to the L2 function on the cylinder. And its inverse operator is the following. It's also explicit. If you start with a function on L2 of the cylinder, you can reconstruct this phi by integrating the family of harmonic function in dt. So these are family of harmonic function, which will depend on u, of course, also depend on rho. It's a harmonic function in dt, and integrating up, we can think of as if reconstructing this phi by putting up layers of harmonic function on dt. So as probabilist, when you see this isometry, like the first excitement comes with, okay, like you have a, here on left-hand side is a Dirichlet energy. If I randomize it, by randomize, I take orthogonal basis and multiply by independent Gaussian, sum them up. On the left-hand side, you get Gaussian free field, zero boundary Gaussian free field. And because this is isometry, it tells you on the right-hand side, if you do the same thing, you will get white noise on the cylinder weighted by 2 rho. And it's just tell you that the Dirichlet Gaussian free field can be disintegrated into white noises, can be recomposed as white noises on the cylinder and go back and forth. But this is a somehow generalized result by Hedemon and Minen, and just a side remark. But once we have this disintegration isometry, then the proof is very quickly that if you have the winding function, recall the rho is in this form, and you just show this by this disintegration isometry, it's a particular form of the winding function is like this, and then you check that the L2 norm, the isometry, the L2 norm is explicitly this way, and it's exactly 16 times of the Loewner energy of rho. So this is the McKee tool, and once we have that, everything falls into places. Sorry for running over time. Let me just show you the final slide about the conclusion of the lectures. So we have SLE kappa. For the small kappa, you get the Loewner energy rate function, the rate function. And SLE duality relate SLE kappa to SLE 16 over kappa. And the large deviation gives you another energy called Loewner energy. This is SLE duality. And we have a lot of results about how these two energies are related. And they're related by this object, like foliation by Weil-Petersson quasi-circles. And there's also another player in it, is that it's all related to a Dirichlet energy of the winding function is actually coming from another part of the story about random conformal geometry, is the coupling between SLE and Gaussian free field. And so the Dirichlet energy of the winding function is exactly the large division rate function of a small multiple of Gaussian free field. And yeah, so if you want to know more about, I have recently written a survey paper about large deviations of Schramm-Loewner evolutions. And the talk of today I discussed is, for this paper is about the large deviation of radial SLE, and for the foliation result it's joined with Frederick Bicklin, and it's in this paper. And and the last reference is, the last reference is about the result on the relation Weil-Petersson quasi-circle and Loewner energy. Yeah, so I have a question. What is a GFF? GFF is a Gaussian free field. I didn't enter into this part of the story. So the Gaussian free field is like the version of Brownian motion where time is becoming two-dimensional.